And the volumes all the way down. So, just a quick announcement, there will be no office hours today on Zoom. So, well, only one person is on Zoom right now, but if you want to meet on Zoom, then maybe we can do that on Monday if it is urgent, or next Thursday. Okay, so last time we learned something truly important about the relationship between maps and divisors. So let's do a recap. Last time we were doing the following. We noticed that if we have a non-zero map phi that goes from SE to RD, okay, so the setup was that we had a finite extension. So this was finite, meaning that S is finally generated as an R module. We have a finite extension between normal integral domains. In this case, this means that these are integrally closed in their respective field of fractions. So we like to think of the map of the spectra to be F. Okay. So we have this finite cover between R and S. We care about the case in which F is Frobenius, right? This for now. So we have this, and so here you're going to have E a divisor. You can say either that E is a divisor on spec S or over E. That's maybe the way to say it. To say over S, and D, let's put it here, D is a divisor over R. So let's say that you have a phi over here that is R linear. So this is an R module, this is an S module, but by restriction of the scalar, it's an R module. So suppose that you have this non-zero map. It has to be non-zero for this. So to this map, you can attach a divisor, dv. So the other day we started with this divisor dv has two key properties. Right? It is effective, and it is linearly equivalent to the relative canonical divisor that actually the other day we were calling RAM. Okay, so I think I'm going to switch notation if you let me do that for many reasons, but the first thing is that, well, it really doesn't matter because these two things are not quite equal, they are linearly equivalent. But it's more in the sense that the relative canonical divisor is an equivalent class, you know, like as the canonical divisor is. But I think for the sake of the clarity, I think I'm gonna keep using the relative canonical divisor instead of writing right. So here we have plus the fullback of D minus E. That's what we have. So this information here is equivalent using the language of classical algebraic geometry, saying that d phi is an element of the linear system of this divisor. Given any divisor, its linear system, well, you can say its full linear system is the set of all effective divisors in its equivalence class. Okay, so to a map, there corresponds a phi. Okay, and so, and actually this mapping is surjective. Okay, so we have a surjective map to, let's say, to this linear system. Any divisor with this property is hit by a phi. Okay, so here we can write relative canonical divisor minus pullback of V, sorry, plus pullback of V minus V. Okay, and well, I guess on this side, what we're going to have is the following hum. It's hum, let's say, push forward of SE, comma, RD. Well, we have to take non-zero maps, okay? So we have to delete the zero map. And so certainly, two phis can have the same divisor d phi. Okay? But the only can happen, so the point is that, let me write it down over here, d phi equals d psi if and only if phi equals psi times a unit. So unit of S. Okay? So in other words, U belongs to S times. So S times here denotes the unit of S, which is a multiplicative group. And so what happens is that you have the action of this multiplicative group on this set, and the quotient happens to be isomorphic to this linear system. Okay? So this is very generally the correspondence between hums, this type of hums, and divisors. Okay? So this is the more conceptual part of the picture, and this is, let's say, the more computational part. So that is the recap, I think, from last lecture. Any question with this? So we're going to denote this correspondence by phi goes to d phi, the divisor of phi. Okay.
In this case, these are not finite dimensional spaces, right?
No, these are huge spaces. These are modules. Yes. If you were to have, then maybe perhaps a projective already, then they start to become finite dimensional.
And one do this in the homogeneous case, or let's say if the data was homogeneous,
yeah,
you could do this. This is a homogeneous map, or I mean, does it preserve degrees?
Mm-hmm. There is certainly a way to do that, but it's a lot of work in the sense that you have to do a lot of bookkeeping. But yeah, you can do this in the homogeneous case, and you have to keep track of degrees very carefully. The main thing here is that this pull forward is delicate in terms of keeping the degree. But yeah, certainly you can do this in a homogeneous way, and you get results of this type for projective varieties, for example. Yeah, so you can start, so the case we care the most about is the case in which you put Frobenius here. And yeah, you can do that, but Frobenius mess up with the degrees quite a bit. In the sense that you have to consider different gradings, not a Z grading, but a gradient modulo Q and things of this sort. But yeah, in principle, you can do that. So, okay, let's see. Let's do, so remark. And by remark, I hope you know now that it means exercise. So this is exercise 5.44. The notes, for example. So So you may be wondering, what does this tell me about phi? What does the phi tell me about phi? And so the point is that in the language of schemes, what phi is a so-called section of this module. So you have a map that sends a linear map that sends 1 to phi, and therefore, since it is S linear, you completely determine the map. So the point is that you want to know whether or not phi is a generator, a free generator of that Helm set. And so that happens. So this is an isomorphism, right? In that case, this whole Helm set would be just phi times S, right? So this happens if and only if the phi is literally 0.
So as S modules or as R modules?
As S modules. As S modules. So in a sense, this is why I just tell you where to send 1. Because since it is S linear, it's determined by where 1 goes. Yeah, so this is a section of this module as an S module. Okay? And so phi will generate this Helm set if and only if the phi is 0. And so what's happening, well, you got to do the exercise, but you know that here you're comparing S2 modules. So whether or not this is an isomorphism is determined in codimension 1. And so you go and look at the prime divisors. You can localize every single prime divisor, and you can look at whether or not phi generates that Helm set. And actually, the evaluation of phi, let's say, at that specific prime divisor, will give you the coefficient of this phi. And so it's telling you how far away phi is from being a generator. Okay? That's what this divisor tells you. And so the divisor is 0. If and only you actually have a generator. Okay? The divisor tells you, in a sense, how much phi knows about the whole Helm set. It is a test on how knowledgeable phi is. Okay? So, moreover, I'm going to let you do as an exercise the functoriality of this. So suppose that you have a tower. You have a tower of maps, and let's say that on the spectra you have F, and over here you have G, let's say. And moreover, let's say that you have 3 divisors. I guess here we have D, here we have E, and we would like to put F, right? D, E, F, but F is for use. So let's say G. So 3 divisors. And suppose that you have maps TG. This of course are normal integral domains, all of them. TG, SE, and RD. So here we had phi, but let's take another one, C. Of course, different from 0. So you're going to have the composition over here, right? This composition is going to be phi composed with C. And so what is the natural question? How do you compute the divisor of a composition? In terms, of course, of what is the right order? So let me put it here, d phi and d psi. How do you do that computation? How do you understand that? Forget it, look at this. Sorry, people on Zoom. So we're exploring the functoriality of these divisors and keys, right? The divisor of the composition should be determined between these two. So let's see what you need to do. So this divisor lives on T. It's a divisor over T. D psi is a divisor over T2. So these two can be compared. But this one is an issue, right? Because D phi is a divisor over S. So to compare to them, we need to lift it up to T. And the word for lift it up is pullback. So maybe it's better to write pullback here. So here you have it in a sense the product of two maps. It has to be equal to, any guess? What operation would make sense here? The sum. Okay, so this is the functoriality. D of the product is the sum of the D's, which is the canonical operation between them. So it is functorial, let's say. Okay, so that's gonna come as a very useful thing because remember, we want to apply this to Frobenius. And when we do this to Frobenius, the magic of Frobenius is iterative a lot. Okay? Now let me switch notes and use new ones. So okay, let me just finish this part with a little bit of notation. Notation / definition. We define the relative canonical module of F, or we can also write omega of S over R. Simply, well, it would be the upper streak of R, which is R is comma R. And actually, what justifies the name, let me do it here, is that we just saw that there is an isomorphism between this and S, and what goes here? The relative canonical divisor that we call, let me just be here, so let me say that we call KF, but what it is by definition is KS minus the pullback of the canonical divisor of R, right? We saw the other day that there is an isomorphism from here to here, to this home set. So this is why we're going to denote or call this module the relative canonical module, because it is S of the relative canonical divisor. Okay. Okay. Now let's get interesting results out of this formalism. So let's apply this. Let's apply this to the most beautiful finite cover in the world, which is Frobenius. Okay. So still, we're assuming that R is an integral domain. In particular, it is reduced, and so the Frobenius well, is injective. So you can think of it as an inclusion. So it is a finite cover. Well, and we're going to assume that R is a finite, so that the Frobenius is a finite cover. So assume R is a finite, so that Frobenius is a finite extension. Okay, this right here is the single most important instance for which a finiteness is important for what we're about to do. So because then, well, one more hypothesis, right? So, and also, or very famous hypothesis that F upper streak of omega R is isomorphic to omega R. But remember that this is very minor. This happens in the most important cases we care about, the case in which R is local, or if R is an algebra that is finally generated over a field. So if R represents the array, essentially, right? So this happens. And so remember that we like this hypothesis because what is the meaning of this hypothesis? The hypothesis gives us automatically a Cartier operator, right? It gives us kappa R from omega R to omega R. And remember, if, well, since R is S2, because it is assumed to be normal, then this kappa E generates the following concept. Then we have an isomorphism between this ring and the Hom set. This is a property that any abstract trace has. But the Cartier operator is just specifically the trace of Venus. So it has to have this property as well. You remember we were saying the other day that the trace knows all Homs between the canonical modules. Okay, so we have this. But of course, we want to write omega R equals R kappa K. So that's what we're going to do. So the first thing, let's move to the other side, is to compute a relative canonical of Frobenius. Let's see what it is. So what is the relative canonical of Frobenius? Well, Frobenius is a map from R to R. It is an endomorphism. So what we have to do is to take the canonical of this part, and we have to pull back the canonical of this one. What did we say this is? What is computed the pullback along Frobenius is simply multiplying by Q. Right, so this will be Q KR. This is 1 minus Q KR. Remember this number. Okay, it's gonna come up all the time. Okay? You will see the beauty of this number that looks so innocent. So let's keep this in mind. The next ingredient we need is the traces. So we're gonna take the trace, because we just put E, D, and it's gonna be the operation. So it's gonna be the Cartier operator. So what I'm writing down right now is just notation. I'm gonna take any divisor D, and I'm gonna call this. So this is by definition the Cartier operator E tensor R minus kappa R with D, reflexify. We did this the other day with an like general F general little f instead of just Frobenius. So I just repeated myself so that we refresh everything, okay? I think it's important to go slow on this. Also, I think it may be rather mean for you. I'm sorry, people of Zoom, I keep forgetting. Moving this around. So we have this, and what is this map? This is going to be a map that goes from where to where? Well, it goes from here. Remember, this is just little f. And so here we're going to have the relative canonical, which we know that now to get this, right? This shows up here because it's a relative canonical of Frobenius. So here we're going to have QD and RD. This is just a pullback of D along Frobenius. Okay, and so this is going to be the traces of Frobenius now. Are going to be these maps. And then the following is an isomorphism. So I want to tell you what are the homes. Let me see. Did I? Okay. No. This is here. Oh no, yeah, we're good. Sorry. No, you cannot see. Okay, right here is good. So what are the homes from Frobenius push forward RE to RD? We accomplished this the other day, and this is going to be isomorphic to the Frobenius push forward of R, and I will have to write down a very careful divisor here, y minus q kr plus qd minus e. Remember, we started the class with this relative canonical plus pullback of d minus e. I'm just writing down here what we started with today, but instead of little f, I'm just using Frobenius. And the fact that this is the relative canonical Frobenius, and the pullback by Frobenius is just multiplication by q. Okay? How does this work? If you give me little s, I can see a typo here, this goes to this trace here times s. But I want to emphasize the following. The fact that this trace here is deep down the Cartier operator. It's just a twig of the Cartier operator. Remember how on Tuesday I was saying that maps like this are very plastic, and you can, mold them from one type of domain to another type of domain, right? By twigging. So we just did that to the Cartier operator to get this trace. And what we're saying here is that every map here is essentially the choice of an S by which you have to multiply the trace. But more conceptually, this tells you that the Cartier operator is very wise. And it knows all possible maps between a Frobenius push forward of a divisor to another divisor. Through this isomorphism explicitly. Right? And so if you may be expecting, so why are we doing this? Because we're looking for Frobenius splittings. Okay? So this is telling you that the source of all possible Frobenius splittings are going to be coming from the Cartier operator, which can be tweaked and molded into different traces, and the choice of an S. So, but the source of everything is right here. Okay? This is the brilliant observation. Okay. Any question with this? So this is something that would be very good if you can really spend some good of your time like really trying to conceptualize and understand, very, very well how this works. Okay. So, okay, let's see why this is useful. So the next thing we can do is to say, okay, I can now look at well, I'm gonna take non-zero things here. Let me remove 0. I'm gonna remove 0 from here too. Because I know that when I remove 0, I can understand very well the elements here. Because now these are elements of the field of fractions of R, where I can compute diff. Okay? And so moreover, I'm going to have an action by the group of units of R. And same here. And I can take the coordinates. This isomorphism respects that. It's a homomorphism, and the action is homomorphic. And so when I do that, I get an equivalent between a linear system, right? This is a linear system, and this Homs. So let's write this down. So I'm gonna have this real quick. Let's write this down to see what happens. Okay. So on the left-hand side, we are going to have the linear system. The linear system 1 minus q kr plus qb minus e. That's this linear system. Okay? And on the other hand, well, we're going to have what we have. We're going to have maps from here, identified up to that. Yeah, so there isn't much to do, so let's just write it down. Let's remove 0. And let's identify maps that are obtained from one another by multiplication by units. And we know that identification is good for F-singularities, right? Because that shouldn't change anything. It's just multiplication by a unit. So it's essentially the same map up to some isomorphism of the ring, endomorphism of the ring. Okay, and so this is the correspondence here. So to a phi, we're going to attach a d phi. What are the fundamental properties of this d phi? One, it is effective. And second, it is linear equivalent to whatever shows up in here. So I'm going to write it down as 1 minus q kr plus qb minus e. And so phi goes to d phi, and this is a bijection of sets, just sets. Okay. And you may be thinking, okay, so what? Who cares? And so, well, I suppose Carl Schreed look at this and, have a light bulb lighting, and he noticed the following. So he said, okay, let's look at that carefully, and let's do a couple of things. Let's look at the case in which what is the case I want to do? Let's suppose that D equals E, just for fun. What do we have? Well, we would have an equivalence or a bijection, sorry, or a correspondence between ERD maps between here and here, non-zero maps, right? Non-zero maps is important. And we're going to say that two maps are equivalent if they're obtained by one another by multiplication by units. Okay? So to a phi, I'm going to associate a d phi that is effective and linear equivalent to, now what do we have? We have 1 minus q kr, right? Plus, let's say minus, or what is the right thing to say, I guess, plus q minus 1 d. Again, sorry, people of Zoom. Right? Did I do the math correctly? We get that, right? But let's make it look even prettier. So I'm gonna say that this is divisors, d phi, and I'm gonna move this to the other side. So I'm gonna have, let me do it like this. Q minus 1 kr plus d phi is linear equivalent to q minus 1 d. Well, I guess the one that is effective is this one. But we have it, right? What is obvious about this? We're looking for beauty here. What is all that? The coefficients, right, is q minus 1. They're like, let's divide by that. Okay, so set, or set, set delta phi equal to delta phi 1 q minus 1. Where does this live? It is a divisor, but it's no longer an integral divisor. It is, but it is a q divisor. It has rational coefficients, but even better, the coefficients are prime to p. So this is what is the notation? Is a divisor with coefficients in zp. What is zp? Is a localization of z at p, but you can think of cp inside q, right? As all the fractions such that p doesn't divide them. Like that. So it lives there. Right? Then what happens? Well, this is effective, right? It's a positive number saying this was effective, this is effective. Right? It is effective, and now the equality becomes kr plus delta phi is linear equivalent, not over z, but over zp. So we use this notation to d. And well, this is brilliant because this is the bridge between F singularities and the singularities of the minimal model program. Because now this should start resemble a boundary. For example, if you just go to the library and take a book that is called Singularities of the MMP by Jonas Polar, just open a random page, and the expression KR plus delta is omnipresent, it's just everywhere. The neural equivalent often over Q to something else. And that's the bridge. So F singularities are singularities of the minimum of the program because of this relationship. Okay? This puts F singularity into context. And the singularity of the minimum of the program are singularities about the canonical divisor. And so this makes explicit every time you choose a phi, you are telling me something about the canonical divisor and its properties. You took a phi such that you can do a deformation, or let's say you make an alteration of the canonical divisor for it to become something else that you may want. Okay? It could be zero, it could be something that maybe if we're playing globally, it's ample or something. And that's the game. Okay? So let's write this down carefully. And that is the Schritt's correspondence. Part 1, because very small. And that's the bridge, really. Okay. So to recap, if we have a non-zero phi, okay, from here to here, right? Then to this phi, we're going to attach a delta, which by definition is the d phi divided by q minus 1, and it is an effective ZP divisor over R. It has the property that when you add it to the canonical divisor, you get something that is ZP linear equivalent to D. Oh, there's a typo here. So many typos. I'm so sick and tired of typos. No, I think I fixed it already because I'm using all notes. So my question to you is, when is it that two phis define the same divisor, delta? Well, if so, question. When is it that two divisors, two phis, let's see how this is not obvious, because now I'm going to vary the E. Now we're going to start iterating for Venus and look at the dynamics we get when we let E vary. Okay? Let's take two maps. Let's use the Spanish notation now. When is it that delta phi is equal to delta C? Now it's not so obvious because E and D are different. Okay. So let's see. So first of all, let me define the power of phi. What does it mean to raise phi to the k power, which we have done already, right? So this is the following map. So I'm going to start writing it down the other way around because, yeah. So phi is a map that goes from here to here, right? So if I push it forward, then it's gonna go from E plus E to ER. Okay? Now I can push this forward again. And now it goes from 3 E R. Okay? And I can do this until I get to K E T R, sorry. So this thing I wrote here is a composition that goes phi composed with this phi composed all the way to, we stop at K minus 1 E. And this is going to be a map that goes from KE to R. And that map is denoted by EK. It's a K power of phi. If you forget about our linear structure, is literally the composition of phi with itself K times. The push forwards that looks like some weird thing is just to keep track of the R linear action. Okay? Now we're getting into Cauchy algebras territory. Are you with me? So this is the power. So the second power would be P composed with this. The third power would be this. And so exercise using form to reality. And this is the brilliance here. This is important. Delta dk is going to be equal to delta P. Because by functoriality, delta pk is going to be, you're going to have to sum the people, you're going to have to pull them back all the time. So if you do the calculation, this is going to be q k minus 1 plus q k plus 2, which you have to do. Please do the calculation, write it down, convince yourself that this is true. This is a truly important calculation. Q plus 1 dv. But who is that number in secret? It is Q, we learned it in elementary school, right? Q minus 1. dv. Who is this in secret, in disguise? Delta P. And if you move this to the other side, you get delta pk. That was Carl a great realization. It's simple, but it's great. It's delta who carries the information, not d. Like we want to think of phi and phi to the k to be the same because they're sort of trying to tell us about the same Cauchy algebra. And the reason they give it the same delta. Okay? And of course, if I put the unit here, well, it doesn't change because the unit doesn't change the divisor. So, I've told you there's two ways in which two divisors can define the same delta. Could there be another way? The answer is no. So let me write down this definition. P, we're going to say is delta equivalent psi, delta equivalent if so let's say that this lives in degree D, in degree E. So let's say this belongs to, but let's say this is a non-zero map between here to here, and let's say that this is also non-zero, but this one goes from D or D. Okay, let's say you have two different maps where E and D vary. Okay, that's the magic. Okay, let them vary, and so if we say that they are equivalent, if they have a common multiple, let's say there exists an integer n that belongs to the common set of multiples of E and D. Right? This is the ideal in Z generated by E, the ideal in Z generated by D, which is other way to say about the multiples of E and D. So let's say that there is a common multiple such that now I'm going to raise phi to the n divided by E, because now this lives in degree n, right? Equals psi n divided by D this time times the unit. And these two maps here goes from n RD to RD. By what we just said, then phi and psi define the same boundary. Right? Because the boundary or the delta of this map is the boundary of phi, and the one of this one is the one of C. So they have the same delta. And that's the only thing that can happen. So this is the theorem / exercise. I think it's very actually important that you do this. You convince yourself that this is indeed the case. So, fact exercise. Phi is delta equivalent to psi if and only if delta phi equals delta psi. We just prove one direction essentially. This one is fine, and I'm telling you that the other one is true. That's the only thing that can happen. So, in particular, one more thing. So what from this you see actually that this is an equivalence relation on what set? You can take the set, let's say this joint union perhaps, that this joint union of these modules, I could have written down at the very sum if you want, but I only care about the structure of sets. And so this is an equivalence relation in this set. Okay, so this thing here defines an equivalence relation. Well, and this tells you essentially what, right? Because we see that two maps are the same, if only they have the same thing here. So from this should be straightforward that it's an equivalence relation. Okay? So here is the next ingredient we need to conclude. So now my question is, well, what is the quotient of that equivalence relation? To tell you what it is, I just need one more ingredient. So the next ingredient is a very pretty observation. Let's come back to Z localized at P. Let's look at Z localized at P. What is this? Well, let's think about it geometrically, right? So this is the stock of Z at the prime ideal P. So it is a co-limit of the open neighborhoods around P. So in principle, what you do is that you look at all of these rings. So these rings are also called like Zn. But I don't like that because it's really confused with p-adding numbers. So let's use Z adjoining 1 over n inside Q, right? So these are all the fractions in which in the denominator you have powers of n, right? So you have this colimit, and you take this colimit over n. This is well defined because this is a colimit that is taken using the relationship of divisibility, right? So, like for example, C1 over 2 is inside C1 over 6, and C1 over 3 is inside C1 over 6. So Z1 over 2 and Z1 over 3, they meet at Z1 over 6, and so on. So that's how this colimit works, right? However, the observation is that, well, this is a colimit, so we can take subsystems of open neighborhoods, right? What is the one that we're looking for? So look at this. This freaking Q minus ones. What I claim is that they know all about divisibility or prime to P divisibility. So you take the colimit now over E. This set of open neighborhood is just a subsystem inside Q. And what I'm claiming is that they give you the same limit. Because it's a cofinal one. So exercise. It's a really pretty exercise. It's pretty basic, like elementary arithmetic on how divisibility works. So if I ever teach a course on ring theory, this is going to be in the exam for sure every single time. Okay, so you have that, and this gives us an understanding of what this really is in terms of these Q minus 1 that show up all the time. So with these two ingredients, we are ready to conclude. So if we take this set here, so this is the theorem now, the Schwitz correspondence. Part 1. It says that if we look at this set, the disjoint union of this whole maps, when we let E vary, we fix D, right? D is fixed. So let's look at all these maps. Okay, let's remove 0. 0 is unknown. And let's look at the quotient by, let me do it here, delta equivalence. Right? We identify the two maps that have a common power that differ by a unit, essentially. Right? And so now we can say what this is. So the mapping that takes P to delta P. Here, what do we get? We get the set of, let's say, effective ZP divisors, with this notation D ZP R, such that KR plus delta is ZP equivalent to D. Well, the theorem is that this is a bijection. Let's see. Isn't it beautiful?
Yeah.
Effective ZP divisors such that when you add them to the canonical divisor, it gives you D, well, the equivalence class. This is the exact same information as a phi from here to here, And well, the phi is not unique, it's unique up to saying that the common power, blah, blah, blah. That's it. And so this is by rational geometry, or the minimum model program specifically, let's say MMP, sub, let's say Morris program, F-singularities. That's a bridge. How you embed F-singularity theory inside Morris program. So it puts them into context, but also like it opens your eyes on what you should be doing. Okay. Any questions with this? So, well, I think essentially I told you how the injectivity part works. It's just like this equivalence relation. And for the surjectivity, you use this. Right? Because what does this mean? This means that there exists an element here, or let's say something that you inverted, so that you multiply both sides and you get an equivalence relation. But the point is like, when you look at what are you inverting here, you're inverting elements like this. So you're always multiplying by q minus 1. That's it. For some e sufficiently large and so on. So then you get the bijection. This showed up, I think, the first time in a paper called F adjunction. And we will see that if we have time. And so the point is like there is this very important thing in rational geometry, especially in the MMP, that is called adjunction. And so in which you want to descend data across devices. And so you want to descend this type of data across devices. It's very difficult. And so the F adjunction, what it does is I said, like, if your data looks like this, it's rather tiny, that you can hook up a phi out of that, and the phi is super easy to descend. It's intrinsic to F-singularities to descend, as we will see. And then you descend on this side, and then you come back to this side. So the F adjunction works like you start here, you go here, you adjunction here rather trivially, and then come back, for example. But yeah, that would be something for another day. It's probably after the break, a big break. Any questions so far? So now let's look at, I guess, the correspondence part 2. Where we another typo. It's crazy. Yeah. Need to fix this one. Wait, whatever. The typo is exercise 549. So exercise, what does this delta p mean? So if you have p, and here a section, let's say it's a free generator. So here it should be D free generator, if and only if the delta p is 0. So that's what delta p is trying to tell you too. How much phi knows about the whole foam set. So let's keep it over there. That's for you to do. Exercise. Here I have a question for you. And it's an honest question. Actually, I don't know the answer. What happens if in the correspondence? So let me just say what happens. I think this could be interesting actually, but I'm not sure what to say. What happens if we replace ZP by the p-adic integers in the correspondence? So this makes sense on the right-hand side of the correspondence, right? You can put any rank you want. But what happened to the left side? On the right-hand side, it gets bigger. Because ZP is inside there. This is the completion of that. So what happens on the left-hand side? So actually, if you think about it, ZP is a co-limit. And that co-limit part is reflecting the set that you take all possible E's. You move E. So here now you do a completion, which is it's a limit in a sense. It's over the ring. What happened to the left-hand side? I don't know actually. I don't know, could be interesting. The other thing I've been wondering for a while is like the total opposite. What happens if instead of ZP you put ZP? It's like the complementary. This will be wild divisor. On one hand, so when you do prime to p things, you're doing 10 things. You're removing like bad things because in characteristic p, but dividing by p is bad. So you want prime to p things. But what would be the wild side of the story? Why didn't you take divisors that are over here? These are the numbers that look like this, right? So these are the wild things where everything is divisible by p. I don't know. I feel like there is a hole there, but I don't know how to fill it out. You can try to see if you can come out with something pretty to say. Just to finish all this correspondence stuff, let me put a part 2 of the thing. I don't think I'm going to go through it in detail right now. Because it's analogous. It's just same thing. We're being a bit more careful. So remember that at some point it's okay. Let's do the case in which E equals Z. Now let's do the case in which what is it? D equals 0. But E is not 0. So let's do the case D equals 0. So what this means is that if you have a P that now goes from here, remember that you have RD, right? Now D is 0, so you have R. To this thing, there corresponds a delta P, which is going to be effective delta P, that is a ZP divisor, such that Q minus 1 times KR plus delta P is linearly equivalent to E. What is the consequence of this if you think about it? So if E is Cartesian, then what are we saying? We're saying that this divisor is CP Cartesian. Then KR plus delta P is ZP Cartesian. Because there is a prime to P number, Q minus 1 is prime to P, such that when you multiply this by this divisor by this number, you get something that is Cartesian. That's what it means to be ZP Cartesian. You may have heard in the context of being Q Cartesian, right? Or this is to say that the pair R comma delta is log ZP Gornian. That would be the terminology you can use. So, so this gives us the definition of a chain boundary. Yeah, so if you again go and open the book by Collar on the singularity of the MMP, you will see it's all about boundaries, and there you will see the definition of a boundary is a Q divisor, is an effective Q divisor delta, such that when you add it to the canonical divisor, you get something that is Q Cartesian. So here we have the same thing, but instead of using the rational numbers, we use ZP. It's a tame version of that, so it's even better. So definition. a tame boundary delta, well, it's an effective divisor, let's just say this. Like that, KR plus delta is ZP corrective. Or i.e., the pair R comma delta is log ZP Gornstein. That's what you're looking for. Remember our Cartesian divisor. Yeah, for example, what is the Cartesian divisor trying to tell us? It tells us about the complexity, or let's say it tells us how far away we are from being Gornstein. At least as far as singularities are concerned, right? The complexity of K measures that. And so we want things to be Gornstein as much as possible. So what we're trying to do is to add something, right? So look at, for example, what we're doing, the coefficient of delta, we're living between 0 and 1. So this is like, in a sense, like a small deformation of K that at least a multiple of it will be Cartesian. So it's like having something that is logarithmically Gornstein. This log makes sense in terms because, you know, this is about differentials, and so what you're doing is like adding dx plus divided by x, which is like the differential of logarithm. So that's where it's coming from. Okay, and so that's what you're trying to do. You're trying to take your device and you're trying to deform it a tiny little bit so that at least a multiple of it, a relatively nice multiple, i.e. prime to b, becomes Cartesian. And then you can pull it back and you can do a whole bunch of things to write down your theory. Okay, so this is the very, very first step. To add a boundary. So in general, a boundary is the same thing, but instead of ZP, you put the rational numbers. In positive characteristics, we need to be more careful. Somehow we want to get rid of divisibility by P, because that's gonna be a headache otherwise. Actually, things start to be false. Okay. So the correspondence. Okay. So what is the point? To a phi from here to here, we add a boundary. So this is a tame boundary. Just to conclude, there would be a similar story. We would say that, okay, let's take phi from here to here non-zero, right? So be non-zero. So we say that phi is boundary equivalent, let's say that to psi, if well, it's a bit more complicated to write down, unfortunately. But let me write down the answer and then like to do as an exercise. First of all, there's a common multiple of E and D. Right, you can see that this is always looks like a co-limit thing, that you have to find this common intersection. So such that, let me write down like Pn minus 1 divided by P E minus 1. And now you know where these numbers are, right? Because E divides N. So this is gonna be like, call K N over E. So this is gonna be P to the K minus 1 plus P to the K minus 2. So these numbers are very concrete thing. This is just like a shorthand for it. So this is an integer in particular. It's not a rational. Well, it's a rational number, but it's an integer. Okay, so it's not like a fraction. You know what I mean? Pn minus 1, Pt minus 1. So E and D are linear equivalent after multiplying like this. So this is the first condition, and so the point is, well, end. Now you can write down Pn minus 1, Pe minus 1, E is equivalent, or sorry, it's isomorphic to NR. Now I can compare them thanks to this multiple of 2, P minus 1 P, right? And I'm going to have two maps to R, and this is going to be P to the NE. It's going to be a composition of Phi with itself at times. You have to be careful because you know that you have an E over here, so it's not so clear how you compose. But you can see here and notice how you define this. So here you're going to have C and B, and this commutes. So this isomorphism comes from this linear equivalence. Remember that linear equivalence means isomorphism between these objects, between these modules. Okay, and so the point is that phi is boundary equivalent to psi if and only if they define the same boundary. That's what it's called that. If they define the same tame boundary. And so to finish, let's write down the second part of the Schutz correspondence over here. What do you think is going to happen? So we're going to have a huge set over here. We're going to take this concept and now you're going to do something crazy. You're going to vary E. It's going to be a Cartesian divisor. And E is going to be an integer, positive integer, non-negative integer. Let's remove the 0 ones, okay? We always remove the 0 ones. We take this set, we quotient by boundary equivalence, right? And so we get a map from P to delta P. Well, right, it's well defined because of that. And what you get here are just tame boundaries. The set of tame boundaries. And so when you go and look at, again, the definition of all these singularities, look canonical, low terminal, terminal, PLT, all these sort of notions, they are properties about tame boundaries. Okay, so but in positive, well, about boundaries in general, but for tame boundaries, you have this relationship with phi, and that's how you see the analogy between F-singularities and this type of singularities. Thanks to this correspondence. Every single phi we take is secretly just a tame boundary. Okay. I think we're running out of time. So next time, we're going to start exploring this to define more classes of F-singularities. We're going to use the formalism of Cartesian algebra to build out of this correspondence. And yeah, so okay, goodbye, Jorge.